Hello, and welcome you once again back for the next session on game theory. Now, in this particular video, we are going to have a look at the next methodology, which is most frequently and most prominently used in game theory, and what is called as principle of dominance. Before we proceed to understand how do we basically solve the problems using this principle of dominance, let me give you a brief information about what exactly you mean by dominant strategies, also dominated strategies. In fact, a dominant strategy is the one that will have the absolute best effects no matter what your opponents or partners do. It is basically a set of choices that creates the highest balance of reward and also the risk factors. So it can be either the reward or the risk factors. We also call it as risk ratios. Sometimes there is no truly dominant strategy which leaves you an intra-sensitive situation where your strategy must adapt to the actions of others. Let me give an example. As you all know that chess is an extremely complex game and is purely adversarial, meaning one player must lose for the other to win. So it's almost impossible to create a dominant strategy. You and your opponent are constantly adopting using intrasensitive strategies. On the other hand, the dominated strategy produces the absolute worst result, meaning regardless of the choices made by the other players. Going back to our chess example, some players will randomly advance their pieces, heedless of the risks or disadvantages they create for themselves. So basically, this strategy, right, the dominated strategy, causes the players to lose regardless of how any normal opponent plays. Now, why is this principle of dominance required? For easiness of the solution, it is always convenient to deal with smaller payoff matrices. Fortunately, the size of the payoff matrix can be considerably reduced by using the so-called principle of dominance. Now, what it says? It says that if one pure strategy of a player is better or superior than another one, irrespective of the strategy employed by his opponent, then the inferior strategy may be simply ignored. I repeat, if one pure strategy of a player is better or superior than another one, then the inferior strategy may be simply ignored. In short, it can be summarized as follows. If all elements in a row are less than or equal to the corresponding elements in another row, then that row is dominated and it can be deleted from the matrix. Similarly, if all elements in a column are greater than or equal to the corresponding elements in another column, then that column is dominated and it can be deleted from the matrix. Let us straight away solve certain problems and then try to understand how this principle of dominance actually works. So I have a problem in front of you, and the problem statement says, using principle of dominance, find the best strategy and the value of the game. So I have two players, A and B, with player A having 4 strategies and player B having 4 strategies. And this is my payoff matrix. So first and the foremost thing is what we do is we find out whether there exists a saddle point. So these are my row minimum and this is my column maximum. And then I draw conclusion that this particular payoff matrix do not have any saddle point. Now, since the problem statement says use the principle of dominance, we use the principle of dominance to reduce the payoff matrix. As far as possible, let us see whether we can reduce this 4 cross 4 matrix to the 2 cross 2 matrix. So how does it proceeds? Now there is no hard bound rule whether you should look from the row perspective or you should look from the column perspective. Irrespective of how you look at it, you will always land up getting the same strategy and the value of the game will not differ as well. So I have 4 rows and 4 columns. When I closely observe, I draw this conclusion that row A1 is less than or equal to row A2. Now watch out carefully. Row A1, right, is less than or equal to row A2. What it means? You look at this particular element of first row, first column, right? So let us look at all the elements of the first row with corresponding elements of the second row. So 2 less than or equal to 6. Am I right? Next, minus 2 less than or equal to 1. Then 4 less than or equal to 12. Then 1 less than or equal to 3. Now when you observe closely, all the elements of first row, that is A1, is less than or equal to A2, corresponding elements, right? So once again I'll tell you, all the elements of A1 are less than or equal to the corresponding elements of A2, and hence what we do is we get rid of A1. Watch out carefully. If A1 less than or equal to A2, that means the elements of that row, then you remove A1, right? Now what happens? My payoff matrix gets reduced to this, and it is now 3 cross 4 matrix. Now please be careful when you are eliminating the row or probably the column. Please do not change the row strategies or the column strategies. Meaning I have removed A1 and I am retaining A2, A3, A4. Please do not rename this as A1, A2, A3. Okay, so let it continue as it is available with you. So my original 4 cross 4 matrix got reduced to 3 cross 4. Now my next step will purely depend upon this new payoff matrix 3 cross 4. Now I realize that column 4, that is B4, is greater or equal to B2. See here, 3 greater or equal to 1, 6 greater or equal to 2, 7 greater or equal to minus 3. So all the elements of column B4 is greater or equal to the corresponding elements of B2, and hence I will remove B4. So there's a slight difference. If row is less than or equal to another row, you remove the first row. If the column is greater or equal to the second column or the other column, you remove the first column. So be careful with this relational operator. For row, it is less than or equal to, and for column, it is greater than equal to. So I land up removing fourth column, and then my matrix gets reduced to 3 cross 3. Okay, so from 4 cross 4 it came to 3 cross 4, and from 3 cross 4 it comes to 3 cross 3. Now my focus will be on this particular payoff matrix, and then I realize that B3 is greater or equal to B1. So I'll remove B3 and I get this particular matrix, right? So B3 greater or equal to B1. See here, 12 greater or equal to 6, then 0 greater or equal to minus 3, and 7 greater or equal to 2, and hence I remove B3. So I get 3 cross 2 matrix. Then here I find that A4 is less than or equal to A2. 2 less than or equal to 6, minus 3 less than or equal to 1. So I remove A4, and then I get this 2 cross 2 matrix with player A having A2 and A3 strategy and player B having B1 and B2 strategy. Now if you closely observe this particular 2 cross 2 matrix, this matrix further cannot be reduced. So once we land up having 2 cross 2 matrix, then we have the liberty of using either the algebraic method or the arithmetic method to find out the strategy and the value of the game. So what I do is I'm just applying arithmetic method, even though there's no hard-bound rule, right? It is totally left up to you people to adopt any methodology you want, right? So I'm just applying arithmetic method, but irrespective of the method you adopt, please understand the strategy and the value of the game will not change. So I'm going to apply the arithmetic method to find strategy and value of the game here for this particular payoff matrix. Okay, so this is what I get, right? So minus 3 minus 2 is minus 5, and ignoring the sign I write it here. Then 6 minus 1, 5, I write it here. Then 1 minus 2 is minus 1, ignore the sign, I write 1. 6 minus of minus 3 is 9, so I write it here. Now to get the strategy, as you know, in arithmetic method, we add the oddments and place it in the denominator. So that is what you can see here. Just have a look at it. This is nothing new. It is the procedure that we have adopted in arithmetic strategy. And then I draw conclusion that player A uses mixed strategy of 1 by 2, 1 by 2, and player B uses mixed strategy of 1 by 10, 9 by 10. And I have these four values: A11, A12, A21, and A22. So these are the values. And then I substitute these values in the formula that you are already aware to find out the value of the game. And the value of the game for this particular matrix is actually 3 by 2. Let us also look at one more example, right? So using principle of dominance, find the best strategy. So I have this payoff matrix. I check for saddle point and I find there's no saddle point here. And then what I do is, when I closely observe, I observe that row A4 is less than or equal to row A3. See here, right? All elements of row A4 is less than or equal to the corresponding elements of row A3, and then I get rid of row A4. And here I observe in this particular matrix, column 5, all elements of column 5 is greater or equal to all elements of column 2, right? So I remove column 5, that is B5, and I get this particular matrix. Now in this particular matrix, I observe column 4 is greater or equal to column 2. That means column 4 is dominating column 2, and hence is getting dominated by column 2, and hence I remove column 4. Right? Then once I get this particular matrix, I have A2 less than or equal to A3. So row A2 is getting dominated by row A3, and hence I remove A2. So likewise, I keep removing the rows or columns, right? I get eliminating the rows or columns. And then now look at this. Now this particular matrix is 2 cross 2 matrix. Now if you closely observe, even this 2 cross 2 matrix can be still further reduced. So look at carefully. The first row, right? All the elements of the first row is less than or equal to the elements of the second row, that is A3. And hence what I do is I remove A1, and I'll end up getting a payoff matrix with 1 row and 2 columns. I mean, don't get panic. This is possible at times where the principle of dominance can reduce your matrix not only less than 2 cross 2, but you will end up having only one element, and that is what you will see in this example. Now further continuing, I have this 8 and 7 with 2 columns. Now I observe B1 is greater or equal to B2, right? And hence I will remove B1, and I'll end up getting this. Now watch out carefully. That's the beauty of this problem, right? So I'm just left out with only one element, right? And then I draw conclusion. See, this particular element 7 is with respect to A3 strategy of player A and B2 strategy of player B. And hence the conclusion drawn is player A uses strategy 3 while player B uses strategy 2, and hence the value of the game is 7. So in principle of dominance, please keep on using the algorithm or the steps to reduce the matrix to as much as possible. It is not that once you get 2 cross 2 matrix, you totally ignore the dominance rules and then you implement arithmetic or algebraic method to find the strategy and value of the game, right? So please understand, as long as the principle of dominance can be implemented, shifting to arithmetic or algebraic method is not appreciated and it is not at all accepted, right? So what I'm trying to say is, if from this, if you go and implement the other method to find out the strategy and value of the game, right, not only you will get the value of the game altogether a different one, but you will, in the examination, you will land up losing the marks, right? So please be very careful. It is extremely important that you adopt the other methods only when all doors of dominance principles are totally closed for you. Now, let us have a look at a typical problem here, right? So same thing, using principle of dominance. Now, why I'm calling this as a typical problem is, when you closely observe this particular payoff matrix, you find there exists a saddle point, correct? There exists a saddle point, and then I can just say that player A adopts strategy A2 and player B adopts strategy B3, and the value of the game is 4, right? But please do not do like this, because you have been asked to solve the problem using principle of dominance. So once you are asked to solve it using principle of dominance, you are not supposed to basically go for the saddle point if it exists. Very rarely, but we cannot rule out the possibilities. So that's what I said. Even though you get strategy as well as value of the game, since dominance principle is asked to solve, you need to apply same and get the optimal solution. Let us have some problems for practice. I'll just show you these problems. Kindly make a note of it and then solve it for your own benefit. Let us proceed and look at the last aspect of dominance, right? Something called as statement problems. So far, all the problems that we have seen in game theory, right from the beginning, the payoff matrix was actually given to you. And it was easy for us to implement and find out the saddle point, strategies, values of the game using different methods, and now principle of dominance. But sometimes what happens, or most of the applications in real life, where the payoff matrix is not given, as a OR professional, we have to develop, we have to come out with the payoff matrix which totally resembles the problem statement, right? Two such problem statements I am giving to you people, right, where we'll discuss how to develop a payoff matrix. Of course, I'm not going to discuss how to find the solution, because any of the earlier method that we have discussed, you can implement it to get the solution. So look at this particular problem statement. Player A and B play a game in which each player has 3 coins, 20 paisa, 25 paisa and 50 paisa. Each of them selects a coin without the knowledge of the other person. If the sum of the values of the coin is even, then A wins B's coin. If it is odd, then B wins A coins. Find the optimal strategy for the players. Now, first and the foremost thing is, you have to understand the problem statement and very carefully develop or come out with a payoff matrix. And let me tell you honestly, if your payoff matrix is turbulent, means you land up giving the entries in the payoff matrix as wrong, then neither the strategy will work out properly nor the value of the game. So player A and B plays a game with 3 coins. So I write those 3 coins here. The first coin is 20 paisa, second coin is 25 paisa, and the third coin is 50 paisa. Similarly for player A also. Now what it says, if the sum of values of the coin is even, right, then A wins B's coin, right? If the sum of the values of the coins is even, then A wins B's coin. Now look at this. This is 20 paisa and this is 20 paisa, correct? So it is 40 paisa. So sum is 20 plus 20, which is 40. So that is even, right? So this is even. Similarly, this 20 paisa and this 25 paisa. So 20 plus 25 is 45. So this is odd. As of now, I just kept it blank. Then this 20 and this 50, 20 plus 50 is 70. So this is even. Similarly, this 25 and this 20 is 45. So this is odd, right? Sum of the coins is odd. So this is even, this is even, this is even. All the blank spaces in this particular matrix is actually the sum is coming out to be odd. Now what happens if the sum is even? A wins B's coin, correct? A wins B's coin. So this is even and the B's coin here is 20 paisa. So I put 20 here and 20 here. Similarly, here also A wins and B has got 25 paisa here. So I put 25 in this cell. And here B has got 50 paisa and this cell where A wins, because the sum is even, I put 50 and 50. Now for all the 4 cells which are blank here, their sum is actually odd. And if it is odd, B wins A's coins, right? B wins A's coins. So what is A coin here? 20. So I have to write it here 20. But since we always talk about player A winning and player B losing, I will say here as minus 20. Got it? So similarly, I have minus 25 here, minus 25 here, and here I have minus 50. So this is my payoff matrix for that particular problem statement. Understand it very carefully, go through it, and then once you are comfortable in understanding the payoff matrix, next step is you apply the principle of dominance and solve the game. So that I'm not going to show you here, right? You apply the principle of dominance on this particular payoff matrix and you solve the game and find out the strategy as well as the value of the game. Now moving further, let me also expose you to one more problem statement, right? Now it says very clearly that in a game of matching coins with 2 players, suppose A wins 1 unit of value when there are 2 heads, wins nothing when there are 2 tails, and loses half unit of value when there are 1 head and 1 tail. So the problem statement is determine the payoff matrix, the best strategies for each player, and the value of the game for player A, right? So once I carefully understand this particular problem statement, right? So what I do is I develop my payoff matrix, right? So I have 2 players A and B, right? And of course this is player B, slightly missed out here. So this is for columns are for player B. So what it says is A will win 1 unit when there are both the heads. So this is head and this is also head. So A will win. So it is 1. Wins nothing when there are 2 tails. So this is 1 tail, this is another one, right? So this is 2 tails. So this particular cell belongs to 2 tails. So nothing is 1. So I write it 0. On the other hand, it loses half unit of value when it's a combination of head and tail. So I write here minus half and I write it minus half. So based on this particular problem statement, this is my payoff matrix, right? So once I get this payoff matrix, you proceed further to get the strategies of the players and also the value of the game.